But for the most part, they're not quite identical, but they're very, very similar. They have the same optics too.
Yeah, well, I know they have the same optics.
I didn't even get to this in the first problem to
Yeah,
I tried to whenever I could to get as much parts of credit as possible.
yeah. First problem's definitely wrong. Because
Did you get kind of half your DSS?
I didn't get
yeah.
Oh, I'm like, dang, how did you get all the way? So like completing both problems, I'm like, oh, look, I've done it half.
Make sure that I was.
I'm not necessarily saying if I had that, I wouldn't have been able to complete it. But
Yeah.
that's kind of arrogant to me, but it would help to have extra time.
Well, I also do things slower. Like,
Oh, I do
I
things
have-
terribly slow.
I have tremors in my hand, which makes it harder for me to write. And I need to write legibly enough that he can kind of make out what I'm doing.
Because my handwriting is terrible. If I write quickly, it will be illegible.
Alright.
That's the thing. Because it's
I did do
caused by my tremor.
you did
I
break
can get a
Either this one's wrong
you know.
Mine is me just having shit handwriting.
Yeah.
No. You ready for this exam on Monday?
Yeah.
I didn't want
I mean, you get an analogy, but it's on campus.
make sure that we're all.
Nope.
Yeah. Which part of it?
You have a
Yeah.
full business school. I'm not looking forward to it at all. I am terrible at presenting things, so I'll probably
Eagle Nautics is the point.
DCO, yeah. It's a design concept review, but it's like we build a plan to accomplish a set.
I just took it as like
Pretty well.
Bill, what kind of
That was the challenge a couple years ago. They modified the challenge slightly between years, so that you can't just reuse the same plane over and over and over again. You actually have to go to my ground up every year, which is the point.
They could also just like for the SE formula stuff, they basically require I think they require a design change. Like,
Sorry, what is it? Robert?
I say,
Yeah.
Are you available
Right after this class, I have another After that, 3 p.m. program.
You can reuse like some things, but most of it is going to have to be completely rewritten.
I know ours we can reuse for like a couple of years.
Yeah, no, I was just
Okay, so no one. Alright, so let's begin with the class attendance video. I'm going to,
Like ours is where
I'm going to make it really easy.
what's the expensive parts, you guys?
What kind of expensive?
That's it.
Expensive?
Okay.
I mean, there were competitions, so I would put out this carbon fiber, and it's like $100 to $200 per seller, just for one propeller. And so that's the most expensive. It's really nice, but it's that's for one propeller. It's expensive. Like $100, like, how much in the grand scheme of things, but for one propeller, it's. I mean, a lot of them for one.
Wow. Runs are in.
Oh, like an ECU?
Yeah.
Oh, it's like 4.
Alright, so we're going to continue on Unit B3 discussion.
More funding. I mean, we don't have a full, like, internal combustion engine like you guys. We have a 1,000 watts.
However, interestingly, do you guys know when is the next exam?
A week from today.
Next Monday is the exam, midterm 2. Okay, so just to start to get ready. I think my guess is whatever the material we cover on Friday this week will be included. So I think coverage will be A5, B1, B2, B3. That's most likely. Okay, 4 units. A5, B1, B2, B3. 4 units. Let me repeat. A5,
Three questions.
B1, B2, B3. Any question?
Yes,
Yeah,
so
yeah.
I'm assuming that are we gonna have to memorize the divergence theorem? Or will that?
Those kind of things I'll give you. In other words, a theorem and then like equations that, the rules, like a distribution rule.
Yeah,
You don't have to. But I would expect you to interpret and then understand the meaning and how to use it and stuff.
okay, that's what I was, okay, yeah.
Okay.
What
Any
about,
other
I know he mentioned the divergence and curl theorems, what about things like the
Divergence, current,
Yeah,
those are
he-
theorems, so
he
you don't have
did-
to memorize.
because he
Stokes
mentioned
theorem,
that those will be given to us, what about things like the non-trivial vector algebraic calculation rules? Will those be
like
given?
what the non-trivial vector algebraic.
They're in
what is
Unit
it?
B1,
Okay.
the non-trivial vector algebraic
Like
calculation
what?
rules.
Like what? Let's be specific.
They're in B1, they're in like slide 3 or 4.
Like stuff like that, of course I'm gonna give it to you.
Okay, okay.
But of course, if I give you those things, you probably need to be able to do this kind of thing. Suppose if I give you, okay, find out this, you'll be able to carry on.
Okay.
Yeah, and then like those in definitions, right? The operator, what is the definition? What is divergence? What's curl? Those kind of things. However, I would expect you to know what the heck is divergence of the velocity field in continuity. What does that mean? How do you use that kind of a mathematical expression to express what kind of flow field kind of? Well, of course, it's obviously way beyond than something you can memorize, mathematical sense. That's what I'm interested in. So that's why people say, do I have to memorize? Well, of course, that's something probably minimum. In other words, memorize is like, memorize in English term sort of indicates, making me impression that, hey, I have no clue, but let's memorize it to get, I just want to pass this class. I have no clue, but I don't care. Let's memorize this equation and then hoping that's going to give me a passing grade. No,
Okay,
obviously not. So you don't have to memorize, but I would actually expect much more than that,
okay.
than just the memorization. That's what I'm usually, reply back to students. Memorization is like, usually use that term, suppose if you are taking math class, you have no desire, zero desire to take that class, but somehow I need it, I have to pass, so I memorize. I have no clue after I graduate. Did you have that kind of feeling? I had that kind of feeling when I took flight mechanics class when I was an undergrad student. I memorized through, I got an A, I had no clue after I took that class. Of course, the teacher was pretty, anyways. So funny thing is when I taught flight mechanics class, like last semester, actually entire year, I had to study by myself, everything, because I had no clue. So now I realize, oh, now I'm rediscovering what the heck does that mean, this equation kind of thing. That's interesting, refreshing, experience. I guess you have to ask yourself, can I teach even arrow to if you have a baby sister or baby brother, can I teach my baby brother or baby sister about aerodynamics? I'm teaching from Dr. H right now. That means you know aero. So teaching something to someone is going to indicate that if you really understand or not, because people, if people don't understand the heck of it, how on earth that person can teach you anything? Okay? It took me like 10 years to understand aero. So early days of my teaching aerodynamics at Emory Aero, I probably didn't have much clue of what I was teaching. It's fact, okay? I try to be honest. So give a new people a slack, okay? Don't be too harsh, even though they cannot teach. Okay? That's common. I was one of them. Any question about the midterm exam too? Professors grow because you are very good students. Okay? We appreciate that. Go ahead.
Is B3 homework going to be due after the exam or before?
I don't know. It depends on how I cover today. Okay. So let's just make a decision by probably Friday, You may argue back and say, well, Professor, you couldn't finish up Unit B3. Why don't you cut off that material you didn't cover? We don't want to see that in exam. Or Professor may say, well, I don't care. You can run it. I tested whatever kind of thing. Or it could be you can push back and successfully saying, well, you know, the coverage is up to B2. It's up to you. I'm flexible. It's your exam. It's your education. Go ahead.
A similar format, 3 questions just about?
Yeah, 3 questions. But each question could potentially be part A, part B, part C, part D, part E. Could be. Of course. If so, it's going to be 2 points each.
Part G.
No, it's not going to be A, B, C, D, E. 2 points each. It's very maximum stretch I can do. Any other question? I try to be reasonable because that's what you see in homework, right? Okay. So if I happen to choose that kind of problem out of homework, of course you're going to see 5 questions out of problem. 2 points each. Okay. Any other question? I try to be reasonable. I'm not going to test out something I didn't teach. That's a terrible sin a professor can do against students.
Can you talk to some of my other professors?
You have to speak up. But well, if I say something, if I complain to admin, they don't care. But if student complain, they care about it because you're the one paying money. I'm not. Anyways, any other question? Bottom line, I promise you, I'm not gonna test you out if I don't feel like I taught you enough. But something, if I repeatedly emphasize in class, I give you homework, I give you quiz, and if you cannot do that problem, that indicates that you have no clue. You can't pass, just like that. So again, you know, try to understand the concept in this class. Okay. Any other thing? Any other question? We're gonna continue. Okay, Unit B3. So Unit B3, we continue superposition of uniform flow and source. Let's just make sure what we're doing to begin with. So you are going to, by the way, superimposing uniform flow and this is the coordinate origin right here, point O. Okay, so coordinate origin, either Cartesian or polar, you are going to place a source. Magnitude is lambda. Okay, if you superimpose uniform flow and then source of magnitude lambda, you are actually going to create a flow field, something like this. You are going to define a solid body in a flow field. So this is a solid body. This is something called half Rankine body. And then this is going to stretch to the infinity. Okay. And then simulated flow field, of course, you're interested only in the flow field around your body. So flow gets in, flow over it. Flow gets in, flow over it. Flow gets in, flow over it. And then some of the flow actually goes straight into the node right here, creating stagnation point. This is the location velocity v equal to 0. And then you can, of course, determine the equation corresponding to it. It's called equation of stagnation streamline. So this particular thing goes through stagnation point. Now, this streamline actually slide over the body surface and flow away. So this is going to effectively define the shape of your body. This is the stagnation streamline. Okay. Also, another important thing is you actually define the node radius here. So this is the distance measured from coordinate origin to the stagnation point. Node radius R, capital R. That's the node radius. Node radius. Okay. So last class we determined little r over capital R, which is the function theta, which is essentially you are going to define this body shape. Body shape coordinate R, normalized by nose radius R, is essentially pure function of angle theta that is going to effectively define your body shape. This is task 1 of your project 2A. Okay? And then this is the equation we got. And then, again, this equation is based on the radians. Okay? So let's be careful. So this is radians. So if you plug in angle theta for the range of 30 degrees all the way to 180, you can convert this degree into radian and plug into this equation to get out of R values. What does that really mean? Well, theta equal to 30 degrees out over R is this much distance, little r, divided by capital R. So it's just a normalized number, which is the data point here, 45 degrees. Data point here, 90 degrees. Data point here, 135 degrees. Data point here, 135, 150, 180. So those are the data points you're going to compute as a function of theta. This R over R is a normalized location of the surface points, normalized by the nose radius. So by connecting those lines with the straight edges, you are going to actually represent the shape of the body. That's something you have to do for task 1, project 2A. That's what we are doing. Okay. Now, before we move on today in last class, I actually flip-flopped this ratio, little r over capital R, flip-flop to capital R over little over R. This is extra step, and then you're probably wondering why do you need to do such a thing? You're going to find out today, hopefully. Okay? If you don't pay attention, you may not be able to find out. You're going to find out. I'm not going to tell you now, but you're going to find out. Go ahead. Question?
So because R over R at 180 degrees
Yeah,
on the graph,
it's right here.
yeah, because that's 1,
1.
is that saying that at all the other angles that the distance from the origin to that point is whatever the value is?
Yeah, this is 1, which is little r equal to capital R. This
Yeah, and
distance
then
is 1.
when you, like,
This one is different. This one
Yeah,
is
if you
different.
scroll up, can you scroll up a little bit?
Scroll out.
So like where it says 90 degrees, so does that mean that the radius from the origin to right up above is
That's
1.57?
1.571. That's right.
Okay.
So this figure is not drawn to the scale, but should be this shape. No.
Okay.
Go ahead, Robert.
Just for that code, the coordinate system, are we using polar or
This is polar, yes.
so polar coordinate?
Polar coordinate is r and theta.
Okay.
Everything is right now.
So when we're graphing this on MATLAB, we're using polar coordinates.
You can use either polar coordinate or Cartesian. You have to do a transformation coordinates though, if you want to do Cartesian. Yeah.
Okay.
Okay. Sure. So today, let's just, based on this fact, we found, okay, so those are the locations of the surface, body surface, okay? So this is the equation of a body surface. Based on that, each coordinate of R over R, which corresponds to 30, 45, 90, blah, 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 angles. What are the pressure coefficients? Let's find out. So let's begin with the pressure coefficient equation. What is it? That's right. So pressure coefficient Cp, original definition is P minus P infinity over Q infinity. This is the original definition. Now this is potential flow field. So this is 1 minus B over B infinity squared. So what you need to be doing is, what is the velocity here? Of course, it's 0. What is the velocity here? It's not 0. So you have to find out velocity at each location, and then plug that in here. Okay. So what is the velocity field? Velocity field is, of course, this is ER, plus B theta, E theta. So this is what? B infinity cosine theta. Oh, okay, plus lambda over 2 pi r, this is BR, plus B theta is minus B infinity sine theta. This is E theta. Okay. So this is the velocity field given in polar coordinate. Okay. So let's find out what is magnitude. Magnitude is a square root of square of each component of both. So you can say magnitude of velocity square is equal to magnitude of BR square plus magnitude of B theta square. You can say that. So let's just take that and find out. So this is the magnitude of B square is, magnitude of BR is B infinity cosine theta plus lambda over 2 pi r, this thing square plus minus B infinity sine theta, this thing square. And I want to do something here. I want to do something. Especially this term. This term is, I have a concern of this term. Okay. So let's think about for a moment, what is lambda over 2 pi r? What is capital R? Anybody, do you remember? What is the definition of capital R? Capital R is, okay, lambda over 2 pi b infinity, isn't it? So from this fact, can you rewrite this lambda over 2 pi r? Eh? This is what, b infinity times, what is it? Big R divided by little r, isn't it? Is that right?
Yes.
That's why, so again, that's why I kind of flip-flop capital R over little r. Okay, that's the reason. Because CP actually uses the equation, that actually equation is a function of capital R over little r. We have to flip-flop. Anyway, okay, so that's why. A little bit of secret. Now you know. So now let's move on. So we're going to move on. B squared is equal to, this is going to be actually given, this is B infinity cosine theta plus B infinity times capital R over little r square plus, this minus goes away because if you take a square, this is going to be B infinity sine theta square. Okay. So this is going to be, okay, B infinity square goes outside of the bracket. You are going to put cosine square theta plus 2 times capital R over little r cosine theta plus capital R over little r square this thing square plus sine square theta, right? Okay. So now, well, you know one thing.
Professor,
Go ahead.
did you drop for the, where you have plus negative b infinity sine theta squared?
This
Yeah,
minus drops off because if you take a square root, it's square.
okay.
So this term is here. This term is still here. Is that correct?
Yeah, I
That
just
sounds
didn't
good.
know if the, where the.
Now this minus goes away because theta square. Anyway, cosine square theta plus sine square theta is equal to 1. Okay? So yes, you're going to simplify a little bit more. So moving on. So velocity square is equal to, okay, this is going to be 1 plus 2 times capital R over little r cosine theta plus capital R over little r squared. Okay, so what is Cp equal to Cp?
V
Sorry,
infinity
V
squared.
infinity. Sorry. I know. Something. V infinity squared. Okay, sorry about that. So Cp is equal to 1 minus V over V infinity squared. This means 1 minus of course 1 minus V squared over V infinity squared, right? So from here you can say what is 1 minus V squared over V infinity squared. So this is 1 minus whatever the term inside of the bracket. Is that right?
Yeah.
Do you follow? What is it? So conclusion, minus 2 R over R cosine theta minus R over R square. This is what you got. Sorry, I'm running out of space. This is the Cp, correct? This is the Cp. As you can see, Cp is a function of capital R over little r. That means it's not quite the same as first. Well, okay, I have to flip-flop this result. Then use that flip-flop value inside of this Cp equation. That's why I have to flip-flop. Okay. All right. So if you use this equation and then plug in theta value from 30 all the way to 180, be careful, this is radian, you're going to have a result of Cp distribution over the surface at each location. Okay? So out of those 1, 2, 3, 4, 5, 6 data points over the surface, you actually compute the Cp distribution over the surface. Obviously, theta equal to 180, this is a stagnation point. Cp is equal to 1.
1 minus 0, so 1.
Stagnation point. And then Cp cannot be more than 1. 1 is the largest value. Cp can be negative. Now, somewhere between 135 to 90 degrees, you have a location where Cp becomes 0, right? What is the Cp equal to 0 point? What does that physically mean?
Velocity is equal to free stream velocity.
You can say that. And then pressure becomes what?
Free stream pressure.
Free stream static pressure. So this is called static pole. You can make a blue one. Okay. So here's an interesting question. Suppose I can ask you, okay, so determine the location of the static pole over the surface of the body. You have to find out location set Cp equal to 0. What is the corresponding angle theta? You can, of course, easily determine such a thing. That's called static pole. I can easily create an exam problem saying, determine the static pole location. Can you handle it? You cannot handle unless you know and understand the concept, right? Again, next exam, I'm going to focus more on if you understand the concept or you have no clue, either way. Question?
Okay, what did you just say about, you have to know the starting point,
Starting point, what is the starting point?
or stagnation point, you're saying?
Stagnation point, okay.
We have to like know that for the exam.
Stagnation point is a velocity 0 point. You defined it and we found it, right?
Yeah.
Throughout the mathematical process. We found it.
Oh, oh,
We found it, yeah. We did it. You remember that? We found the stagnation point mathematically,
Yeah.
right? So you can determine the stagnation point, of course, mathematically. Okay. This is the whole point. Potential flow theory, 100% mass, you can determine stagnation point, you can determine velocity field, you can determine velocity distribution over the surface. If you know, you can determine pressure distribution over the surface. You can plot the Cp distribution over the surface. You can determine Cp 0 location, that is called static pole. You can determine lots of things. Everything is purely mathematical.
Yeah.
Okay. So by the way, let's take a look at a handout. this whole thing is given as handout, okay? So if you are going to do project 2A, task 1, I think, you should look at this handout. Unit B3 handout. Which one? This one? Not this one. This one? Not this one. Sorry, Unit B4 handout. Unit B4 handout. Huh? Oh, okay. Unit B4 handout. Sorry, be careful. Okay, Unit B4 handout. Sorry, I accidentally traced in Unit B4. So if you are not here today, I guess you might miss it. Who's not here? Where's Peter? Anyways, it's your decision either tell him or not to tell him. Okay. So this is exactly what I did in the class. Okay. So this is task 1 of project 2. So this is theta degrees 10 all the way to 180 with increment of 10. You can have more data points if you want to. Okay. I just used the Excel spreadsheet. You can do the same thing using MATLAB. So this is theta angle theta. Then you have to convert it to radians and plug into your equation of R over RCP. Of course, both of them we derived it to that. Right? Mm-hmm. Okay. So those are both a function of theta, of course. And then corresponding degree, this is a transformation coordinate because everything is computed in polar coordinate. Now you're going to convert it to x and y Cartesian if you want to plot it x and y, right? And then you can plot it. I plot it using Excel spreadsheet, but you can do the same using MATLAB, of course. So obviously, this is stagnation point. This is top half of the body. This is a completely symmetric shape. Okay. So if you take the angle negative values, it's going to create the bottom half of the body anyway. So this is the body shape. You're going to plot R over R all the way to theta equal to 10. Go back to 180. This is stagnation point. This is coordinate origin. This is the node radius. Okay. So node radius looks like I took it. Node radius equal to 2. Okay. So everything's normalized anyway. However, go ahead.
So to plot the bottom half, all you need to change is the angles, not the
Like I
equation.
said, angle is there. The bottom half.
Okay, so just the angles.
Angle, yeah. Because take a look at the equation. Its equation is purely function of theta, right?
Mm-hmm.
Okay. That's fine. And then this is the CP distribution over the surface. Obviously, this is also completely symmetric on top and bottom surface. So CP equal to 1 at stagnation point. So this is the product CP, negative value in positive y direction. This is, again, standard for CP plot in arrow. Let me just introduce and emphasize that when you plot CP negative in positive y direction, this is standard of aerodynamics. I'm going to be super picky about this. If you don't follow this, I'm going to take huge points off. This is a standard of aerodynamics. Do you know why? Somebody please tell me why we have to plot like this. CP equals 0. And then what kind of information you are expecting to see this kind of plot? This is pressure distribution. CP 0, and then CP becomes smaller value, and then smaller value, and smaller value. Do you think pressure is increasing or decreasing? Pressure is increasing or decreasing? Pressure decreases as you move along the surface. This is called favorable pressure gradient. Okay? So it depends on the body shape. As the flow flows over the surface, depending on the shape, you are going to encounter either favorable or adverse pressure gradient. Which one do you like? Suppose if you are born like small tiny air particle here, your life starts here, you hit the body flow over, and then your life ends here kind of thing. Do you prefer favorable pressure gradient or adverse pressure gradient? Which one do you think you enjoy your life? Obviously favorable pressure gradient. This is your, I don't know, first day of freshman at Embry-Riddle. Everybody's so nice as you move, you know, visit lots of occasions, people are so nice. you are very happily moving. Then around here, you actually start taking engineering class. Well, statics, oh my goodness, statics, that's a real engineering class. And then solid mechanics comes in, and then fluids comes in, and then, oh my goodness, dynamics comes in. What is that? As you try to move forward, pressure goes up, pressure goes up. What's that? Advanced pressure gradient. Do you write that kind of lifestyle? Well, as you're turning homework, more homework comes up. Okay, as you take the exam, another exam comes up, more difficult, more materials, even materials professor didn't even cover. Oh my goodness, you get more frustrated, stressed out, and then your life becomes more turbulent and turbulent and turbulent. And of course, laminar to turbulent transition starts to happen because of advanced pressure gradient. If the pressure is favorable, well, your life is smooth. Everything's laminar. Here we go. Okay, laminar flow. And then once you hit the advanced point, you get transition from laminar to turbulent, more chaotic, random, trying to kind of hang in there, because turbulence flow have a tendency to stick more on the surface. However, suppose if you get too much pressure, what happens? If you get too much pressure, you do this. I quit. Damn it! I'm not going to do this anymore. You snap it, your flow separates. Flow separation. Here we go. I'm not going to flow anymore. Give me a break. Okay, pressure is too high to flow. Okay. So flow separates. Flow separates. What happens if flow separates? Temporary relief from all the pressure, creating vacuum spot, right? So, but actually, depending on the shape here, though, you may have a chance to, okay, reattach later, and then somehow graduate. Anyway. Then you go visit professor's office and Professor, I'm so sorry, I had nasty attitude. I had too much things. Of course you know. Then professor said, yeah, sure. Welcome back. I'll give you a second chance, Okay, anyways. So that's something you can understand by looking at pressure distribution. Pressure distribution is everything in aerodynamics. So that's why you actually design the shape of the cross-section of a wing. Why do you create such a shape? You want to control the pressure gradient. Pressure gradient is essentially the shape you design. That is going to control the behavior of the flow field. If you do a poor job, you may induce early flow separation. Right? If you do a great job, you may retain more laminar flow over the surface to minimize the cruising drag. Okay, it's a small, tiny thing, but it's going to have a huge impact. So, anyways, so why CP negative in y direction anyway? If you plot both upper and lower surface, okay? If you plot like that, if the pressure goes like this, it is going to indicate lower than atmospheric pressure. So again, you're going to later, you're going to see CP distribution over flow over airfoil, okay? Then you're going to see plot like this. So this is upper surface, this is lower surface. Upper surface usually is lower pressure. Lower pressure is upper side. Higher pressure is lower side. Pressure difference. What's that? This area is called lift coefficient CL. That's fine. Okay, so the pressure difference between upper and lower surface plotted on CP plot is going to determine total lift you produce of the cross section. That's fine. So you're going to see those things later. Okay. Do you have any question about this? This is quite interesting, very fast step of your project. Okay. Lots of important things like why CP plot, how to plot, and what's the meaning of CP kind of thing. Go ahead.
So is the CP distribution plot also inverted then as well? So
I guess so, yeah. So when you plot the CP, always CP negative in plus y direction. I probably specified in the project statement.
Yes.
I think so, yeah. So please follow that. If you don't do it, I'll take a huge points off. Huge points off. Okay. Because no one accepts it as a CP plot in aero community. Okay. Any other question? Okay, so, and also this handout also shows, hey, this is a mathematical toy I've been showing you. So this is an ideal flow machine. For the flow of a circular cylinder, this is the project 2A. You're going to plot this kind of thing in MATLAB. Of course, you can do it. Then suppose later, if you actually start spinning your circular cylinder, you're going to alter the flow field. So you are going to actually introduce the stagnation point here, moving downwards, and then stagnation point becomes here, and then separate from the surface. Now this is the stagnation point. Now at that point, equation of the stagnation streamline does not represent the body surface. Okay, so you are going to see this kind of things later. But this is unit B4. Don't worry too much about it right now. It's just to get the B3 done. B3 is this thing. Okay. So take a look at the handout, okay? Let's move on. Let's move on. So important thing about doing project 2A, please finish up your homework first. Without doing homework, do not jump right into the project. Homework actually makes you think and build the mathematical fundamental. Okay, so two more solutions of Laplace equation. We looked at uniform flow and source and sink. Two more. One of them is doublet. Doublet is a source and sink actually at the same location. Left-hand side is source in this case. Right-hand side is sink. But doublet actually comes up with the direction. If the direction of the doublet is in a negative x direction, you have to add the negative sign. Let's be careful. If you put the source on your right-hand side and sink on your left-hand side, it's going to be a positive doublet. This is actually, I'm showing, this is negative direction doublet. Doublet's direction is negative x direction. Now, this kappa is a magnitude of the doublet. This is combination of two source and sink pair. Okay. So again, as usual, we are going to use, this is a solution of Laplace's equation called doublet. We're going to use psi, probably. And then, of course, once given psi, this is polar coordinate, right? R and theta based. And then you can determine velocity in polar coordinate system. Of course, you can do a coordinate transformation to completely transform this equation into x and y. Of course, you can do that. Number 4 is a vortex. Of course, you looked at it already. So this is a point O, again, mathematical singularity point. And then vortex, we are going to define the direction. This is clockwise, yeah. Yeah, okay. Clockwise is a positive, that's the positive. So if you see a vortex into this direction, it's actually negative. And then this is the solution of Laplace's equation called the vortex. Okay? Now, I think you looked at one of the examples way before. I think Unit B2 trying to find out circulation, right? Do you remember the circulation equation? Circulation equation, somebody please? You guys did homework too. Yeah. Negative line integral over the closed path C, velocity dot product ds line vector, or negative integral over the closed surface S, vorticity del cross B inside, take a dot product the S area vector. So this is circulation, isn't it? Yeah. Okay. Now, circulation gamma is the magnitude of this vortex. So vortex is a very important potential flow solution of Laplace's equation to casually add the flow field to circulation anytime and anywhere. That's why we are going to work on flow over circular cylinder with spin. Spin is essentially you are going to actually add the vortex with a magnitude of gamma. Gamma gives you a circulation of a flow field. That is going to indicate, okay, without circulation, flow field of a circular cylinder is going to be like this, completely symmetric. But if you add the vortex, all of a sudden you are going to simulate the flow of a circular cylinder with spin. It creates the rift, okay? This is called circulation. So this is very, very fundamental practice that every aerodynamic students do. This is potential flow theory application of the circulation theory. Circulation gamma is a magnitude of vortex. Okay? So do you remember this? We did this, right? Right? Recall unit B2. Do you remember that? Do you want to take a look at it once again? Let's take a look at unit B2. Note, okay. Unit B2, we did this practice. Circulation, yeah. We did that. Okay. So you know how to integrate line integral. Okay. Do you remember how to integrate to find out circulation? Integral over C B dot ds. In this case, okay, this is theta equal to 0, theta equal to 2 pi, right? So this is negative integral theta equal to 0, theta equal to 2 pi. What is the velocity? Velocity is Br only. No, not that the Br, B theta. B theta only. B theta E theta, correct? Because it's vortex. Dot product against what is ds?
1 over r d.
Ah, d is theta. Right? Do you remember this? This kind of thing is something I want to test on you, because this actually brings you conceptual understanding, yes or no kind of question. Right? Then as a result, of course, depending on the flow field velocity, but you can determine circulation. Correct? You remember this? And then you did the homework too. Okay? Homework was this kind of flow. Line integral. This is this kind of integral. Either way is fine. One is easier to do polar. One is easier to Cartesian. Anyways, so having done this, let's go back and take a look at once again here. So this is exactly what you're seeing here, okay? So this is negative integral from theta equal to 0 to 2 pi b theta e theta. This is velocity b. This is ds. Okay. Then finishing up this integral actually gives you the circulation. Circulation is basically 2 pi r b theta negative. This is circulation of a point vortex. Which is gamma. Okay? So picking up this solution of the Laplace equation, you can casually add the circulation to the flow field. That's what you're going to do, project 2B. Now you're going to try to spin the circular cylinder by adding circulation to it. Okay? Any question here? So next class, now we are going to superimpose uniform flow and doublet to construct flow of a circular cylinder without spin. Now, you can guess. If you superimpose uniform flow doublet plus one more, it is going to give you flow of a spinning circular cylinder, which is unit B for what is it? Vortex. So if you superimpose vortex with circulation gamma here, you are easily going to simulate the flow of a circular cylinder with a different rate of spin. Low rate of spin, medium rate, and high rate of spin, and then it's going to keep changing stagnation point from here to here to here, depart from the surface, and then producing lift per unit span. Okay, so that is the lift producing mechanism. Circulation theory of aerodynamics, you can actually use it as is almost, theoretically speaking, for the simulation of the cross section of a wing. Circulation theory. We are going to get to it. Do you have any question here? Go ahead.
Please, scroll to the previous slide.
Okay, let's go. Okay.
Yeah, it's.
Okay, yeah.
It's too high.
Anything else? Go ahead.
When you're defining the circulation of the vortex flow, and you have the angry no with the 3 question marks next to your surface integral,
Yeah, the bottom is
you see the no on the bottom of the page, the in the box,
In the box.
the line above that,
Right up.
above it with the 3 question marks on the angry no.
Yeah.
Why is that the case?
Because this is a potential flow, irrotational, that means this is 0. So
Oh,
you
yeah.
cannot determine
It's an indeterminate integral.
indeterminate integral, that's right. The only
Okay.
thing you can determine out of this is some kind of constant, that's your conclusion. You cannot determine that constant itself. That is homework.
Yeah.
Right, yeah. That is homework, B2 first thing or something, I don't know.
Yeah, it was like the first or second problem.
Yes,
too.
as a homework.
I just wanted to recall why that was the case.
Yeah. Okay. Indeterminate integral, because you cannot integrate 0. The only thing you can say is some kind of constant, that's all I can say, but indeterminate. Any other question?
But integral is 0, so we know that.
No, the integrand is 0, but integral itself could be 0 or could be non-zero, some kind of constant. That's the only thing we can say, that's why. Okay, great. Anything else? Okay, we're gonna see you back on Wednesday.